In this lecture, we will find the area of the green shape in three different ways. In the drawing, we have a circle. We know that the radius of this circle equals to 5 units, and the angle ACB equals to 60 degrees. Tangent CA is tangent to this circle at point A. Tangent CB is tangent to the circle at point B. And we want to find out the area of this green shape. So we'll start with the first method. We will define the center of this circle as point O. Then we will join together points A and O by a straight line. Actually, OA is the radius of this circle that equals to 5 points, to 5 units, because line segment OA starts from the center of the circle and ends at point A, that is a point on the circle itself. Therefore, OA is the radius of this circle. We will join together points B and O by a straight line. For the same reason, OB is also the radius of this circle that equals to 5 units. And we actually have a rule. The rule states that, rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to its tangency. I will read rule number 1 again. Rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to its tangency. So if we have a tangent to this circle, so BX is tangent to this circle at point X, and if the radius of the circle is drawn to the point of tangency, that is to say to point X, then the tangent BX will be perpendicular to the radius, that is to say this angle will be equal to 90 degrees. Because whenever you have a tangent to a circle and radius that is drawn to the point of tangency, that is to say to point X, then the tangent Px will be perpendicular to the radius, that is to say this angle will be equal to 90 degrees. Okay, so actually here we have we have here tangent CB is tangent to the circle at point B, and the radius, this radius is drawn to the point of tangency, that is to say to point B. Therefore, according to rule number 1, the tangent will be perpendicular to the radius, that is to say this angle will be equal to 90 degrees. The same thing is in the other side. Tangent CA is tangent to this circle at point A, and we have this radius that is drawn to the point of tangency. Actually, it touches the point of tangency, that is to say point A. Therefore, the tangent will be perpendicular to this radius, that is to say this angle will be equal to 90 degrees. Okay, and we also have rule number 2. Actually, we know that CA equals to CB according to two tangents theorem. Two tangents theorem is actually rule number 2 is two tangents theorem. Two tangents theorem. Actually, two tangents theorem states that actually two tangents theorem states that the lengths of two tangents from a common external point to a circle are equal. So I will read again rule number 2. Rule number 2, that is actually two tangents theorem. Two tangents theorem states that the lengths of two tangents from a common external point to a circle are equal. Okay, so the meaning of this rule is that if you have point D, that is a common external point, and you draw two tangents to this circle, tangent DA is tangent to this circle at point A, and tangent DB is tangent to this circle at point B. Then the lengths of those two tangents will be equal to each other. That is to say, DA will be equal to DB. So whenever you draw two tangents to a circle from a common external point, that is to say from point D, then the lengths of those two tangents will be equal to each other. That is to say, DA will be equal to DB. The length of those two sides will be equal to each other. So, according to rule number 2, that is two tangents theorem, we have in our drawing common external point, that is point C, and from point C we draw two tangents to this circle, that is to say CA and CB. Then the lengths of those two tangents will be equal. That is to say CA equals to CB. Okay? So actually CA equals to CB according to two tangents theorem, that is also rule number 2. Okay, CA equals to CB according to two tangents theorem, that is also rule number 2. In the next step, we will join together point C and O by a straight line. And we will prove that triangle CAO is congruent to triangle CBO. So we will focus on triangles CAO and triangle CBO. We will prove that those two triangles can go into each other. We know that BO equals to AO. Both those two line segments are equal to the radius of this circle, that is 5 units. So AO equals to BO equals to the radius of the circle, that equals to 5 units. It is given us in the question. So AO equals to BO equals to the radius of the circle, that equals to 5 units. And we also know that CA equals to CB according to two tangents theorem. CA equals to CB according to two tangents theorem. Okay, CA equals to CB according to two tangents theorem. And also CO is a common side if it belongs to both triangles. So CO is a common side. The red line is a common side. It belongs to both triangles. So CO equals to CO as a common side. Okay, CO equals to CO. It is a common side. It belongs to both triangles. So we actually proved that all the sides of triangle CAO are equal to all the sides of triangle CBO. Therefore, those two triangles can go into each other according to side rule. So triangle CAO can go into triangle CBO according to side rule. Okay, triangle CAO can go into triangle CBO according to side rule. And from the fact that those two triangles can go into each other, we can conclude that angle OCA is equal to angle OCB. Again, angle OCA is equal to angle OCB according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the corresponding angles, that is to say these two angles, those two angles will be also equal to each other. Okay? So angle OCB equals to angle OCA. So if we define angle OCA as x, then angle OCB will be equal also to x because those two angles are equal to each other. So we know that x plus x must be equal to 60 degrees. 2x equals to 60 degrees. 2x equals to 60 degrees. We will divide this equality by 2 and we will get that x equals to 30 degrees. So each angle equals to 30 degrees. Angle OCA equals to 30 degrees. And also angle OCB equals to 30 degrees. According to the rule, the corresponding angles in congruent triangles are equal to each other, they are equal to each other. And because of the fact that this angle equals to 60 degrees, and those two angles are equal to each other, each angle must be equal to 30 degrees. So we will focus on the right triangle CAO. On the right triangle CAO, we know that tangents 30 degrees will be equal to OB or if we focus we focused on triangle CAO. So here, tangent 30 degrees will be equal to OA over AC. OA over OC. OA over AC. Tangent 30 degrees will be equal to OA over AC. So in this right triangle, tangent CAO, tangents 30 degrees equals to OA over AC. But we know that OA equals to 5 units, so we substitute OA by 5. And we also know that tangent 30 degrees equals to 1 over root 3. So we write down 1 over root 3 equals to 5 over AC. Okay? 1 over root 3 equals to 5 over AC. Here we will multiply this equality. We will multiply this equality by AC, and we will get that AC over root 3 equals to 5. So we got that AC over root 3 equals to 5. Here we will multiply this equality by root 3 and we will get the value of AC. So AC will be equal to 5 times root 3 units. Okay, AC equals to 5 times root 3 units, so we can write here that AC equals to 5 times root 3 units, and because of the fact that AC equals to BC according to two-tangent theorem, BC will be also equal to 5 times root 3 units. Okay? And we also have rule number 3. Rule number 3 states that the sum of the angles in any quadrilateral equals to 360 degrees. Again, rule number 3 states that the sum of the angles in any quadrilateral is equal to 360 degrees. I will read rule number 3 again. Rule number 3 states that the sum of the angles in any quadrilateral is equal to 360 degrees. And especially in quadrilateral ABCO, according to rule number 3, the sum of the angles must be equal to 360 degrees. What are the angles in quadrilateral ABCO? The angles are 60 degrees plus 90 degrees plus 90 degrees plus angle AOB, the size of angle AOB. This angle must be equal to 360 degrees according to rule number 3. Again, the sum of the angles in quadrilateral ABCO the sum of the angles in quadrilateral ABCO must be equal to 360 degrees. So here we have 60 degrees plus 90 degrees plus 90 degrees is 240 degrees. So I write it down. That's 240 degrees plus angle AOB must be equal to 360 degrees. Here we will subtract from this equality 240 degrees and we will get that angle AOB equals to 360 degrees minus 240 degrees is 120 degrees. So the size of angle AOB is 120 degrees. We'll write here that angle AOB, this angle, equals to 120 degrees. So what is the area of triangle AOC? The right triangle AOC. The area of triangle AOC actually this is the sign for area. This means the area of triangle AOC. So the area of triangle AOC equals to the base of the triangle times the height over 2. The base times the height to the base divided by 2 equals to the area of triangle AOC. Again, the area of triangle AOC equals to the base of the triangle times the height to the base over 2. So, what is the base of triangle AOC? The base of triangle AOC is AO. This is the base times the height. The height is AC over 2. So the area of triangle AOC equals to AO times AC over 2. What is the value of AO? AO equals to 5 units according to what is given us in the question. And what is the area of what is the size of AO equals to 5 units, and the size of AC equals to 5 times root 3 units. Okay. So in total, we got that the area of triangle AOC equals to 5 times 5 times root 3 over 2 square units. So the area of triangle AOC equals to 25 times root 3 over 2 square units. 5 times 5 is 25. So the area of triangle AOC equals to 25 times root 3 over 2 square units. And what is the area of quadrilateral ABCO? The area of quadrilateral ABCO equals to the sum of the areas of the two triangles that it consists. Quadrilateral ABCO consists of two triangles. It consists triangle AOC and triangle BOC. So the area of triangle, the area of quadrilateral ABCO will be equal to the area of triangle AOC plus the area of triangle BOC. Again, the area of quadrilateral ABCO equals to the area of triangle AOC plus the area of triangle BOC. But because of the fact that triangle AOC can go into triangle BOC, then the areas of those triangles will be also equal to each other. So the area of triangle AOC equals to the area of triangle BOC. Okay? So we actually can substitute the area of triangle BOC by the area of triangle AOC in this formula. We will substitute the area of triangle BOC by the area of triangle AOC because the areas are equal to each other. So the area of quadrilateral ABCO will be equal to 2 times the area of triangle AOC. Okay? The area of quadrilateral ABCO will be equal to 2 times to the area of triangle AOC. But we have already found out that the area of triangle AOC equals to 25 times root 3 over 2. Okay? So the area of quadrilateral ABCO will be equal to 2 times the area of triangle AOC, that is actually 25 times root 3 over 2. So here we have 2 over 2 is 1, so 2 get cancelled. So the area of quadrilateral ABCO equals to 25 times root 3 square units. Okay? But what is the area of this green shape? The area of this green shape equals to the area of quadrilateral ABCO minus the area of sector AOB. Again, the area of the green shape equals to the area of quadrilateral ABCO minus the area of sector ABO. So I'll write it down. The area of the green shape will be equal to the area of quadrilateral ABCO that we have already found out. This is actually 75 times root 3 or 25 times root 3 square units minus the area of sector ABO. So the only thing that is left to find, we know that the area of the green shape equals to the area of quadrilateral ABCO minus the area of sector ABO. So the only thing that is left to find is to find out the area of sector ABO. And the area of sector ABO will be equal to pi r squared, that is the area of the circle. We know that r equals to 5 units. Pi r squared times 120 degrees over 360 degrees. Again, the area of sector ABO equals to pi r squared times 120 degrees over 360 degrees. We know that r equals to 5, so pi r squared will be equal to 25 pi, and 120 degrees minus over 360 degrees is 1 over 3. So in total we will get that the area of sector ABO equals to 25 pi over 3 square units. And we have already found out that the area of quadrilateral ABCO equals to 25 times root 3 square units. Okay, again the area of the green shape equals to the area of quadrilateral ABCO minus the area of sector ABO. I will write it down. The area of the green shape equals to the area of quadrilateral ABCO minus the area of sector ABO. Okay, the area of the green shape equals to the area of quadrilateral. The area of the green shape equals to the area of quadrilateral ABCO minus the area of sector ABO. So the area of the green shape equals to the area of quadrilateral ABCO, that is actually 25 times root 3 square units, minus the area of sector ABO, that is 25 pi over 3 square units. Again, the area of the green shape equals to 25 times root 3 minus 25 pi over 3 square units. Okay, so we finished with the first method, and in the next step we will find the area of this green shape according to a second method, in a second way. We will define the center of this circle as point O. We will join together points A and O by a straight line. AO is the radius of the circle that equals to 5 units. This angle is 90 degrees as I proved in the first method. OB also equals to the radius of this circle that equals to 5 units, and the radius this angle equals to 90 degrees. We've already proved it in method 1. We will join together point C and O by a straight line. we have already proved that angle ACO equals to 30 degrees in method 1. This angle is also 30 degrees, and CA equals to 5 times root 3, and CA equals to CB. CB also equals to 5 times root 3 units. So in the next step we will extend side CO until it touches the circle at point H. Okay, the touching point between CO and the circle will be defined as point H. Then we will draw a tangent to this circle at point H. We know that edge O is the radius of this circle that equals to 5 units, and we know that the radius and the tangent are always perpendicular to each other. That is to say, we have here two right angles. This angle equals 90 degrees, and this angle also equals to 90 degrees. Then we will extend CA until it intersects with the tangent H. The intersection point between CA and the tangent will be defined as point P. We will also extend CB until it intersects with the tangent. The intersection point between CB and the tangent will be defined as point Q. So we have here triangle. We will focus on the right triangle, triangle CHP. On the right triangle, triangle CHP. We know that the sum of the angles in the right triangle CHP must be equal to 180 degrees. That is to say, 30 degrees plus 90 degrees plus the size of angle CPQ must be equal to 180 degrees. So actually this equality states that the sum of the angles in the right triangle CHP equals to 180 degrees. So here 30 degrees plus 90 degrees is 120 degrees. So 120 degrees plus angle CPQ equals to 180 degrees. Here we will subtract from this equality 120 degrees, and we will get that the size of angle CPQ is equal to 180 degrees minus 120 degrees is 60 degrees. Okay, so the size of angle CPQ is 60 degrees. We will repeat on the same process on the right triangle, triangle CHQ. So in the right triangle, triangle CHQ, we know that the sum of the angles is equal to 180 degrees, that is to say 30 degrees plus 90 degrees plus the size of angle CQP must be equal to 180 degrees. Okay, so the sum of the angles in triangle, the right triangle CHQ equals to 180 degrees. Here 30 degrees plus 90 degrees is 120 degrees. 120 degrees plus angle CQP equals to 180 degrees. Here we will subtract from this equality 120 degrees and we will get that the size of angle CQP equals to 180 degrees minus 120 degrees is 60 degrees. Okay, so actually angle CQP equals to 60 degrees, so triangle CPQ has three angles that equals to 60 degrees, therefore triangle CPQ is an equilateral triangle. Okay, triangle the big triangle, triangle CPQ, is an equilateral triangle. We have new rule number 4. Rule number 4 states that the center of a circle inscribed in a triangle is the incenter of the triangle. So I will read rule number 4 again. Rule number 4 states that the center of a circle inscribed in a triangle is the incenter of the triangle. So, according to rule number 4, we have here circle that is inscribed in triangle CPQ. Therefore, according to rule number 4, the center of the circle that is O is also the center of triangle CPQ. So we can write down that according to rule number 4, point O is the center of triangle CPQ. The equilateral triangle, triangle CPQ. Okay, point O, according to rule number 4, point O, point O is the center of triangle CPQ, the equilateral triangle CPQ according to rule number 4. And we also have another rule, rule number 5. Rule number 5 states that the height from the center of an equilateral triangle crosses the side. When we read again rule number 5, rule number 5 states that the height from the center of an equilateral triangle crosses the side. Again, the height from the center of an equilateral triangle crosses the side. So the meaning of rule number 5 is that if you draw height from the center of an equilateral triangle, then this height will divide the side to two equal parts. Triangle CPQ is an equilateral triangle, and the center of triangle CPQ is at point O. So if from point O you draw height to side CQ, then that height OB will divide side CQ to two equal parts. That is to say, CB equals to BQ according to rule number 5. CB equals to BQ. Okay? CB equals to BQ, but we know that CB equals to 5 times root 3. CB, we have already found that CB equals to 5 times root 3, so from this equality we can derive that BQ also equals to 5 times root 3 units. BQ also equals to 5 times root 3 units. And the same thing is in the other side of the triangle. We have the height OA, the height OA divides side CP to two equal parts according to rule number 5. That is to say, AC equals to AP. AC equals to AP according to rule number 5. AC equals to AP, but we have already found out that AC equals to 5 times root 3. We have already found out that AC equals to 5 times root 3, so from this equality we can derive that AP also equals to 5 times root 3. Okay, AP also equals to 5 times root 3 units. And we also know that the sides of any equilateral triangle are equal to each other. So the size of one side of this equilateral triangle equals to 5 times root 3 plus 5 times root 3. It is actually 10 times root 3. So PQ will be equal to 10 times root 3, and according to rule number 5, we have here the height OH. The height OH divide side PQ to two equal parts. That is to say, PH equals to HQ. According to rule number 5, PH equals to HQ. PH equals to HQ. So if we define PH as X, then HQ will be also equals to X because PH equals to HQ. So we know that PQ from one side equals to 10 times root 3 units. But from the other side, PQ also equals to X plus X. That is 2X. So in total, we will get that 10 times root 3 equals to 2X. Here we will divide this equality by 2 and we will get that X equals to 5 times root 3 units. So here PH is 5 times root 3 units and HQ also is 5 times root 3 units. Okay? And what is the area of triangle, the equilateral triangle, triangle CPQ? Actually, the area of any triangle, if we have a triangle ABC, and we know that the size of side AB is A units, the size of side AC of triangle ABC is B units, and the angle between AB and AC is theta. Then the area of this triangle, triangle ABC, equals to A times B times sine theta over 2. Again, the area of this triangle, triangle ABC, that could be any triangle, equals to A times B times sine theta over 2. Okay? So we will calculate the area of equilateral triangle, triangle CPQ according to this formula. We will get that the area of equilateral triangle, triangle CPQ will be equal to CP times CQ times sine 60 degrees over 2. Okay, the area of equilateral triangle, triangle CPQ equals to CP times CQ times sine 60 degrees over 2. But because of the fact that triangle CPQ is an equilateral triangle, CP equals to CQ because all of the sides of equilateral triangle are equal to each other. So actually the area of triangle, equilateral triangle, triangle CPQ will be equal to 10 times root 3 square because CP equals to CPQ, CP equals to CQ, so it is 10 times root 3 times 10 times root 3 is 10 times root 3 square times sine 60 degrees is root 3 over 2, all divided by 2. So the area of equilateral triangle CPQ equals to 10 times root 3 square times root 3 over 2 times 2. 10 times root 3 square is 300 and 2 times 2 is 4. So I write it down. We will get that the area of equilateral triangle CPQ will be equal to 300 over 4 times root 3. Here 300 over 4 is 75, so the area of equilateral triangle CPQ will be equal to 75 times root 3 square units. Okay, the area of equilateral triangle CPQ equals to 75 times root 3 square units. And what is the area of the circle? The area of the circle is actually equals to pi r square, and r equals to 5, so the area of the circle will be equal to 25 pi square units. The area of the circle equals to 25 pi square units. If we subtract the area of the big triangle, the equilateral triangle CPQ, minus the area of the circle will be equal to the area of the green shape plus the area of the blue shape. Plus the area of the yellow shape. Again, the area of the big triangle CPQ minus the area of the circle will be equal to the area of the green shape plus the area of the blue shape plus the area of the yellow shape. Okay? Okay, so I write it down. The area of equilateral triangle CPQ minus the area of the circle will be equal to the area of the green shape plus the area of the blue shape plus the area of the yellow shape. Again, the area of triangle CPQ minus the area of the circle equals to the area of the green shape plus the area of the blue shape plus the area of the yellow shape. Okay, but as you can see from the drawing, the area of those three shapes are identical to each other. They have the same sides, and the angle between those two sides is equal to 60 degrees in all the shapes. So because of the fact that they have identical shapes, their areas will be also equal to each other. So if we define the area of the green shape as x is the area of the green shape, so if x is the area of the green shape, then the area of the blue shape will be also equal to x, and the area of the yellow shape will be also equal to x. So we have here x, x and x, so x plus x plus x is 3x. Okay, x plus x plus x is 3x, but we want to find only the area of the green shape, that is x, so we will have to divide this expression by 3 in order to get the value of x, because 3x over 3 is x. Okay, so we will divide this expression by 3 in order to get the area of x, because x is the area of the green shape, and 3x over 3 is x. Okay, so we do it now. The area of triangle CPQ is 75 times root 3, and the area of the circle is 25 pi square units. The area of the triangle minus the area of the circle equals to x plus x plus x. Again, the area of the circle minus the area of triangle CPQ minus the area of the circle equals to 3x. The area of the triangle minus the area of the circle equals to the areas of the three shapes, so it equals to x plus x plus x. It equals to 3x, and we want to find out only the value of x, that is the area of the green shape, so we will divide this equality by 3 in order to get the area of the green shape. We will divide this equality by 3. 3x over 3 is x, and x is the area of the green shape. So we will get that the area of the green shape equals to 75 over 3 is 25 root 3 minus 25 pi over 3 square units. That is the area of the green shape. Okay, again, the area of the green shape equals to 25 times root 3 minus 25 pi over 3 square units, because the 75 times root 3 minus 25 pi is actually equals to 3x, that is the area of the three shapes. So we have to divide the area of the three shape by 3 in order to get the value of x, that is the area of the green shape. 3x over 3 is x, and x is the area of the green shape according to our definition, so the area of the green shape equals to 25 times root 3 minus 25 pi over 3 square units. Okay, so we finished to find the area of the green shape according to the second method. Now we will find the area of this green shape according to a third method. We will join together points A and B, and we know that in triangle ABC, AC equals to BC according to two tangents theorem. AC equals to BC. Rule number 2. And we also know that in front of equal sides in the triangle there are equal angles. So those two sides are equal to each other in triangle ABC, therefore the angles that are located in front of them are also will be equal to each other. So those two angles will be also equal to each other. So if we define this angle is x, then this angle will be also equal to x, so because they are equal to each other. And we know also that the sum of the angles in any triangle equals to 180 degrees, so x plus x is 2x plus 60 degrees equals to 180 degrees. Okay, here we will subtract 60 degrees from this equality. We will get that 2x equals to 120 degrees. We will divide this equality by 2 and we will get that x equals to 60 degrees. So x equals to 60 degrees. This angle equals to 60 degrees and this angle also equals to 60 degrees. So actually triangle ABC is an equilateral triangle. Okay, and actually the area of the green shape equals to the area of equilateral triangle ABC minus the area of circular segment AB. Again, the area of triangle ABC minus the area of this shape, that is circular segment AB, will be equal to the area of the green shape. The area of the green shape equals to the area of triangle ABC minus the area of circular segment AB, the white shape. Okay? So, in the next step we will actually, we have already found out that AC equals to 5 times root 3 in the previous methods. BC also equals to 5 times root 3 units. We will join together points A. We will define the center of this circle as point O, and we will join together points A and O by a straight line. AO is the radius of this circle that equals to 5 units. We will join together points P and O by a straight line. OB is the radius of this circle that equals to 5 units. And we know that angle AOB equals to 120 degrees according to rule number 3, that the sum of the angles in a quadrilateral equals to 360 degrees. And so what is the area of triangle ABC? The area of triangle ABC is actually equals to 5 times root 3 square times root 3 over 4 square units. The area of triangle, the equilateral triangle ABC equals to 5 times root 3 square times root 3 over 4 square units. 5 times root 3 square is 75. So the area of equilateral triangle ABC equals to 75 times root 3 over 4 square units. And what is the area of circular segment AB? The area of circular segment AB will be equal to the area of sector AOB minus the area of triangle AOB. Again, the area of this circular segment AB equals to the area of sector AOB minus the area of triangle AOB. Okay, the area of circular segment AB equals to the area of sector AOB minus the area of triangle AOB. We have already found out the area of sector AOB. The area of sector AOB equals to pi r square times 120 degrees over 360 degrees. And the area of triangle AOB equals to 5 times 5 square, that is 25, times sine 120 degrees is root 3 over 2, all divided by 2 is root 3 over 4. Okay, so the area of circular segment AB equals to this expression. R equals to 5, so pi r square is 25 pi. 120 degrees over 360 degrees is 1 over 3. So the area of circular segment AB equals to 25 pi over 3 minus 25 times root 3 over 4. That is the area of circular segment AB. That is the area of circular segment AB. And we know that the area of the green shape equals to the area of triangle ABC minus the area of circular segment AB. And the area of triangle, equilateral triangle ABC actually equals to 75 times root 3 over 4 square units minus the area of circular segment AB, that is actually, here we have, it is actually 25 times root 3, 25 pi. It's actually 25 pi over 3. The area of sector AOB is 25 pi over 3 square units minus 25 root 3 over 4. So the area of the green shape equals to this expression. Here we will open the brackets. 75 root 3 plus 25 root 3 is 100. So the area of the green shape will be equal to 100 times root 3 over 4 minus 25 pi over 3. So here we have 100 over 4 is 25. So the area of the green shape will be equal to 25 times root 3 minus 25 pi over 3 square units. Again, the area of the green shape will be equal to 25 times root 3 minus 25 pi over 3 square units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the area of the green shape. We found out the area of this green shape in 3 different ways. So according to the first method, the area of this green shape equals to the area of quadrilateral ABCO minus the area of sector ABO. Okay? And according to the second method, we found out the area of the green shape. The area of the green shape equals to the area of the equilateral triangle CPQ minus the area of the circle divided by 2, because when we the area of equilateral triangle CPQ minus the area of the circle equals exactly to the green shape plus the blue shape plus the yellow shape. And because of the fact that those two shapes are identical, they also have the same areas. So if we divide the area of the triangle minus the area of the circle, if we divide it by 3, we will get the area of one of the shapes that will be also the green shape. So the area of triangle CPQ minus the area of the circle divided by 3 will give us the area of the green shape. Okay? And that was the second method. Again, the area of equilateral triangle CPQ minus the area of the circle divided by 3 will give us the area of the green shape. In the first method, we calculated the area of quadrilateral ABCO and we minus the area of sector ABO equals to the area of the green shape. And on the third way, we actually subtracted from the area of the equilateral triangle ABC, we subtracted the circular segment AB and we got the area of the green shape. Okay? In the third method, in the third method, the area of the green shape, we found the area of the green shape by the formula that the area of equilateral triangle ABC minus the area of circular segment AB will give us exactly the area of the green shape. Okay? So that is the third, and in the second way, we repeat again the second way, the area of equilateral triangle CPQ minus the area of the circle over 3 will give us the area of the green shape. And in the third method, in the first method, the area of quadrilateral ABCO minus the area of sector ABO is equals to the area of the green shape. Okay? So, in this way, in 3 different ways, we found out that the area of this green shape equals to 25 times root 3 minus 25 pi over 3 square units. Again, the area of this green shape equals to 25 times root 3 minus 25 pi over 3 square units. Okay, thank you very much.